Welcome to the participants and to the speakers online to the fourth webinar in the Natural Capital Seminar Series. My name is Deanna Donovan, and as the environmental economist here at JNCC, I'm the host of the seminar. The seminar today is entitled Beyond Belief, What More by Modeling? Our presentations today will focus on modeling, providing a brief introduction to several different examples of modeling, especially as applied to ecosystem analysis, and examine how this can be useful to assessments of ecosystem services and natural capital. We have three speakers today, each of whom will speak 10 to 15 minutes. I'm happy to say that we're very pleased to welcome an environmental economist colleague of mine from Germany as one of the presenters in our seminar. Today's webinar will be run a little bit differently than usual. In a few minutes, I will hand over to Emma Wright, who will be the moderator for this presentation. She's worked on modeling here in JNCC for several years and is certainly better able to field the questions in this area than I am. Thank you. Emma, it's yours.
Hi there. So for those of you that don't know me, my name is Emma Wright, and I'm a senior analyst in the ecosystem analysis team here. So yes, I do a lot of modelling here. I think modelling is an incredibly powerful mechanism, but for a lot of people it's quite daunting and can be seen as quite complicated. A model of something, of anything, is a representation of something, and almost certainly is a simplification of something. And actually, if you're talking about a model aeroplane, that's true. And if you're talking about statistical models, spatial models, and economics models, that's also true. So the mechanism behind creating the model might be complicated, but the idea is to try and get down to something a bit more simplistic. They can be designed to achieve a range of things. So it might be trying to better explain something, to gain some evidence to support a hypothesis, to help us visualize something. This could be literally in terms of thinking about figures or maps, or it could be more theoretically. And they can be used to predict outcomes and measure change. And because of all this, it makes them a very popular tool in the natural capital world. There's a lot to understand in the natural capital world. There's the supply and demand of ecosystem services, and also the processes and flows behind the services, both within the services themselves, but also between these. And models can help us look at these, both reflecting what's actually there, but also the interrelationship of all of this put together. It means that there's a great many natural capital models out there and ecosystem service models there, and there's a great diversity of tools and mechanisms. And some of that's reflected in the talks today. We have three very different talks. Some of the sort of bigger and larger ones that you may be familiar with are things like INVEST, which is the integrated valuation of ecosystem services and trade-offs, or ARIES, which is artificial intelligence for ecosystem services. And these are all sort of tools to try and assess ecosystem services, perhaps map them, help better make decision tools. Some of them may be very specific. For instance, there's one called ORVAL, which is the Outdoor Recreation Valuation Tool. So it's very complex, but it's just looking at sort of one aspect of ecosystem services. And these can even be brought together. So this week, the University of Exeter are launching their NEVO tool, which is Natural Environment Valuation Online, which is multiple economic models all brought together. And JNCC have been helping support them on the biodiversity side, quite big on those. So a lot of these may be spatial, maybe looking at the outcomes, sort of wanting maps as outcomes, either literally of the services, either the supply or the demand or the flows in between them. And because of the very nature of natural capital, more and more these are incorporating value and therefore economics. Which tools to use can be a complicated question. And the main thing is you really need to consider what the question is that you're asking, what information you're trying to get out of it, and also what data do you have available, because that definitely makes a difference to what you can do with it. These days, a lot of these tools, particularly some of the ones I've mentioned, the bigger tools, they can have quite sort of user-friendly applications. They have a nice user-friendly interface. You don't need to be a technical wizard to be able to use these tools, which is fantastic because it means more people can use them. And particularly when you have more people or organisations It could be governments or even NGOs that are that could use these tools, that could use this information and use this knowledge, but wouldn't have the resources to do it themselves. It's great that there's a lot of these tools out there. But something that really needs to be considered whenever modelling is done is sort of understanding, yes, what we can use them for, but also what we can't. What they do tell us, but what they don't. So you need to know the sort of level of certainty behind what it is that you're producing, and how those results can be used. So this might be very much in a statistical way, what is the probability that these results are correct? It might be more sort of a bigger question. So if you had, for instance, a tool or application which was looking at the effects of where you planted woodland within a region, the output may be very much environmental of where is the best place in terms of producing the highest ecosystem service value. But if that model, as a simplification, doesn't include all the sort of socio-economic or even behavioural factors which would actually be influenced in a decision-making process, then the outcome won't actually reflect what is the likelihood to be true. These, as I said to begin with, though, these are incredibly useful, in particular for change. And you may have noticed that there's a lot at the moment about potential change, something to do with the EU exit and things like this. And so modelling is used more and more to try and kind of understand what might happen, what policy changes might make, what land use changes might make. And for instance, our first talk from James might glean a little bit on some of there's many different ways of asking this question, but what some of these models can help look at change. I need to not talk too much, so we'll start. We'll go straight into the first talk now. So the first one in today, we have James. He's another senior analyst in the ecosystem analysis team, and he will be introducing some of the work he has been leading on, which incorporates Bayesian belief networks as a way of exploring ecosystem services.
Great, thanks, Helena. So yeah, I'm going to talk a little bit about Bayesian networks or Bayesian belief networks. I'm actually going to spend a fair amount of the talk talking about what Bayesian networks are and how they work. So apologies to those who thought they were going to a natural capital talk and actually found themselves in a stats talk. But it's going to be a very simple example and a slightly silly example. And then once you're all experts, I'm going to skim over a couple of examples of where we're using this for actual natural capital work. So Bayesian networks are essentially graphical representations of a system. So you think of the key bits of your system and you put them in as blobs on your graph, and then you draw lots of lines connecting them together based on what bits influence what other bits. And we call the blobs nodes and the lines edges or arcs. And then you can put knowledge of various types behind those nodes, and that could be from actual sampling on the ground, or it could be expert knowledge. And then once you have your network, you can ask questions about what will happen if you do different things to it. So for this very simple example, we're going to ask the question, is James in the office? Am I in the office on any given day? Now, if you ask any people I work with, this is not necessarily a simple question. I work from home quite a lot, and I travel quite a lot, and I have a non-work day each week as well. So that's our first node. That's kind of our output node down at the bottom there. And the first thing we need to do is think, what are the things that influence the probabilities I will or won't be in the office? So two obvious ones are the day of the week. So Tuesdays, for example, is my standard non-working day, so I'm unlikely to be in then. And also the time of day. So I'm not a particularly early starter, and I have quite a long commute, so I'm often not in until maybe 9:30 or 10 o'clock, and then I usually leave around 5:30. So this is our network. We have 3 nodes and 2 edges. The edges have a direction, so shown by the arrows. So day and time influence the probabilities I will or won't be in the office, not the other way around. And once you have your network, you need to list the different states that each node can have. So for the day and the time, that's very easy. If you stick a calendar somewhere at random, you'll hit one of 7 different days. For the time, so time is kind of a numerical variable, so we can divide it up into meaningful blocks here, which makes the network more useful. So between 7 and 9, it's quite unlikely that I'll be here. It gets a bit more likely between 9 and 10, and then between 10 and 5, I probably will if it's a day where I'm coming. And then for our bottom node, whether I'm in the office, that has 2 states. It can be yes or no. I'm either here or I'm not. So once you've done that, you have to assign probabilities to each of those states for your nodes. So obviously the probability that it'll be any given day is 1 in 7. Similarly, for the time, it's fairly straightforward. We're ignoring the night time when the office is closed here. So we have a 12-hour window when I could be in the office, and the probability that a random pin will fall in any one of those blocks is just the number of hours in that block. For the last node, though, it's a bit more complicated because these two nodes are independent. They don't depend on any other nodes. The last one, it's dependent on the state of these two. So you need a probability for each possible combination of states of these two. So we can do that by looking at the probability of any given day as an office day. So I did this initially with some expert judgments based on what I think my work pattern looks like. When I actually compared that to my calendar with some actual data, it was worryingly not that similar. But anyway, so I'm in 60% of Mondays, 10% of Tuesdays, which is my normal non-working day, and so on. And then we can ask, what's the probability that I'll be in the office at any given time, given that it's a day when I'm coming in. And as I said, it's quite likely that I'm in before 9 o'clock, between 9 and 10 a bit more likely, and between 10 and 5 I probably will be, and so on. So then we can multiply those together to get our probabilities for any given time on a given day. And this is called a conditional probability table because it's conditional on the states of the other two nodes. This is actually only half of the table. So this is the probability that this node has a state of yes, that I am in the office, but there's another layer on here. So it's actually a kind of three-dimensional matrix because you need the probability that I'm not there as well, which would just be 1 minus each of these. So once all of your nodes have their probability tables, you can stick those back into your network, and you can get something like this. So this is assuming we have no previous knowledge. So we've been living underground for an indeterminate period of time, and then we're suddenly dropped into JNCC office. We don't know what time or what day it is. If you come and look at my desk, what's the chances I'll be there? Well, quite small, as it turns out. But then as you add knowledge, so if we say we know that it's Friday, we still don't know what time it is, then you can increase what you know about whether I'll be there. So it goes up to 40%. And if you know the day and the time, then it goes up to 60%. So that's kind of how Bayesian networks work. They're relatively straightforward, but obviously, if you have lots of nodes and lots of different states, these conditional probability tables get very large and very complicated, which is why we do it in software rather than manually like this. So some actual examples. This is a network that Becky has largely developed for ecosystem services from arable and horticulture. This is based on some work that was done in Natural England to look at which components of different systems are most important for service delivery. And the nodes, the sort of rectangular nodes down here at the bottom are service stocks and flows and benefits that we get from them. The grey and blue nodes are the components and processes going on in the ecosystem. And that's from the Natural England work. And then up at the top is something that Becky and I have added, which is that the purple nodes are pressures that act on the different components of the system. So we've got things like soil erosion and compaction in there. And the red nodes at the top are the human activities that generate those pressures. So this is quite complicated, but we can take a simplified example just for one service. So this is cultivated crops. So we're saying that crop growth is dependent on soil fertility, which is dependent on soil nutrients and depth and biota, and also on water availability, which comes from the water table, and soil porosity, so how much of the water that falls as rain actually sinks in. There's probably a climate bit in here that we have missed off for simplicity. And then there's some pressures acting, so soil compaction could reduce water porosity, so it means you lose more water as runoff, and it could impact negatively on your soil biota, for example. So once you have your network structure, we looked for some data that we could put behind this, and there's already a spatial layer of agricultural land classification, which assesses the quality of different places based on their soil and water availability and climate for crop growth. So that's perfect. We can kind of short circuit a lot of our network. So then we end up with that feeds in here. This crop growth potential comes from the agricultural land classification map. But then we still have our pressures. So if you have high levels of your pressures, you might expect your actual crop growth rate to be lower than your crop growth potential. And you can put in scenarios and then let the network learn from those. You don't necessarily have to fill in all of your probability tables manually to achieve that. So here are some of our probability tables. So this is just showing that if you have a high level of soil compaction, you'd expect the soil porosity to be reduced. And that would have a knock-on impact on crop growth rate. Then you can put some spatial layers into those. So this is an Environment Agency layer of water resource availability, and we have the agricultural land quality map that we had. And these are raster maps, so there are grids, and each grid cell has a value. You can lay them on top of each other, take the values from the different layers and feed them into your nodes, and it will give you an output value for your crop growth rate in this case. And this isn't a particularly scientifically useful output at this stage, so it's not got much data going into it, but it kind of demonstrates how the system works. So that's that one. And the second example has been in St. Helena. So this is St. Helena. It's out in the middle of the South Atlantic. Here's Peterborough overlaid for scale. So it's not a big place. It has a permanent population of about 4,000 people, I think. And they have a lot of environmental challenges that they're dealing with, which are kind of being exacerbated by an anticipated rise in tourism from an airport that they have built recently. So a team of us, including a few from JNCC and other places, went and developed a network for St. Helena. So this is what it looked like to start with. This was refined through a series of meetings with stakeholders, sadly via Skype from a hotel in Johannesburg for reasons I won't go into now, rather than actually on the island. And then this is the kind of final network. And St. Helena is actually quite data rich, so there's a good habitat map and soil maps and things that we can put into these nodes. And we're not quite there yet, but we're in the process of developing this so that with those data layers and this network, we'll be able to generate maps for these ecosystem services from different bits of the habitat. So I think that's it. Thanks to Becky, who's done a lot of the work behind the UK stuff, and a load of other people involved in the St. Helena bits.
Thank you very much, James. And finally, we will be going across to Frank Wirtzel. He's joining us today from the Brandenburg University of Technology in Germany. And he's going to be providing us with an economist's angle. He works a lot with ecologists, and he's going to be talking about his work using ecological and economic models to design effective agri-environment payments to ultimately benefit endangered butterfly and bird species.
Yeah, hi everybody. Actually, the typical presentation of the software and ecological economic modeling procedure I'm going to present is 90 minutes. So this is a very short version. I gave literature, so if you have questions and want to do further reading, or I'm also happy to answer any questions you may have afterwards, or also if there's no time, send me an email. Okay. You all know intensification of agriculture has a negative impact on biodiversity. The main response actually agri-environment schemes, but there's also hope that organic farming might do something. So mostly empirical ecological research analyzed the impact of organic farming, and well, they're contradicting results. Some research says there is an impact on biodiversity, others says there is none. What do we want to show here? We want to assess the impact of organic farming on biodiversity with a focus on birds and butterfly species, on meadows in Germany, in Saxony, a federal state of Germany, in the context of an agri-environment scheme. And we actually apply ecological economic modeling procedure, and there's a software behind it, which we developed, have been developed over the past actually 10 years or so. And there are other applications. I will come back to that in the end. This is an overview of the modeling procedure, and I will quickly go through the different boxes. We have altogether 15 birds and 15 butterflies, which were selected in previously with the relevant authorities for Saxony. We have an information folder which contains the relevant species and habitats characteristics which we need for the ecological model. So we are talking about grassland and, for example, mowing. So the probability of egg deposition is a relevant parameter that we need to know. It's intuitively clear if you have mowing and there is a bird's nest on the meadow, the bird nest is destroyed. We have mowing and in the software also grazing, but here we focus on mowing, different mowing and grazing regimes. Here we have the following, we have only 3, but altogether in the software there are several hundreds different mowing and grazing regimes. differentiated according to basically the time and the frequency of mowing, but also the application of fertilizer and for grazing, livestock density, but also start of grazing, whether there's a combination of grazing and mowing, and so on. We have landscape information. So we divided Saxony in grid cells of 250 times 250 meters. And we have spatial information on land productivity on the level of these grid cells, soil moisture, but also the elevation. Okay, the ecological model shows the impact of the different mowing and grazing measures on the species. So how does it work? You don't need to understand this equation. I'm very brief, but I want you to understand that the model is able to calculate for each grid cell a number between 0 and 1. 0 means habitat quality in this grid cell is very low. 1 means it is very high. And the model can do this for each species, for each measure, and for each grid cell. How does it work? Here we consider the habitat suitability independent of the timing of measure. This can be predation, but some species also require specific elements like humidity or water, forest settlements, and so on. Here we have for each week the egg deposition probability. And this egg deposition probability is influenced by the timing of the measure. So the habitat suitability depends on the timing of the measure. In our example, mowing, the small graph below shows, so if you have the gray columns are the egg probability distribution. And if you have mowing, and once the eggs are there, the egg is destroyed. And then depending on when exactly the mowing and the egg deposition takes place, there's a probability between 0 and 1 that the nest is destroyed and the young birds are dead. You have also an indirect effect of the timing of the measure. This is influenced, or the relevant part is here whether the grass is high, medium, and low. Some species require high grass, some medium, some low. And the growth of the grass depends on altitude, soil fertility, but also on the timing of the measure. So all these impacts give you, for each grid cell, for each measure with impact on each species, a value between 0 and 1. So how do we go from this local scale, the grid cell, to the regional scale, here Saxony? We sum the values between 0 and 1 for all the grid cells. However, there are two important aspects to consider. One is we have data on species occurrence maps. So actually, in order to have not a 0, the measure, or the grid cell with the measure, must be within the dispersal range of a species. And we consider only a certain value between above a certain minimum threshold. Then we sum up, taking this into account, we sum up the values of all the local grid cells, and we have an effective habitat area, which is the regional ecological benefit. Okay, so we have for each grid cell the impact of each measure on each species. So now we turn to the costs. The question is here, of course, does the farmer take part in an agri-environment scheme? And we assume farmers are profit maximizing and they participate if total costs are higher than the payment they receive. We assume costs depend on opportunity costs. This is the profit loss after implementing a certain measure instead of using the land in the most profit maximizing way. But also we take into account transaction costs, administrative costs, but they are not determined by the modeling procedure, but given as input. So how do we determine opportunity costs? And this is similar to the ecological model. So we look at each grid cell, and we have data for each measure, for each grid cell. What are the opportunity costs? So how are they influenced? We consider we compare each measure with the reference scenario indicated by ref, which is the profit maximizing land use. And the first term here considers that if mowing takes place in a different way, there's a loss typically in energy, in the quality and quantity of hay, which depends on soil productivity, altitude, the timing of measure. And we assume that the farmer have to be compensated by buying concentrated feed. And as we have costs of concentrating feed, we can calculate that. We have also variable costs, for example, cost of fertilizer, and compare the cost then with the profit maximizing reference scenario, and also we consider labor costs. Okay, now we have the simulation. We can simulate the impact of agri-environment schemes on the species, because agri-economic cost assessment tells us which boxes or farmers participate, and the ecological model tells us the impact. And we have also the possibility to do a cost effectiveness analysis. That is, we are in a region, we have a given budget, and the procedure tells us how to design agri-environment schemes that the output for the birds and butterflies is maximized. Okay, now to the problem here. We extended the modeling procedure to take into account organic farming. Of course, there are different economic data that has to be fed into the modeling procedure. And then we simulated a Saxon agri-environment scheme with 3 measures. For example, minimum usage per year is 2 times, and first mowing is not before the 1st of June. Interestingly, the conventional farmer receives 330 euro per hectare, the organic farmer much less. This is because the farmer also receives a subsidy for being an organic farmer, and due to legal restrictions, he cannot get more than that. So we simulated 2 scenarios we have in order to understand the impact. The first one is so-called conventional agri-environment scheme. The whole area is managed conventionally, and an agri-environment scheme is offered to the farmer. And then we have so-called organic agri-environment schemes. The whole area is managed organically, and then AES is offered to the farmer. Okay, first, what are our key results? First, what is the impact of organic on conventional farming on the birds here in the example? And you see the black and white columns are pretty similar except for the corncrake. So there's only little difference. Why is this so? Because although organic farming does some things different, but they are similar mowing and grazing dates. And here we looked at the mowing and grazing dates. So with the model, we are able to identify that. Then we compare the organic agri-environment scheme with a conventional agri-environment scheme, and we see that the conventional agri-environment scheme actually performs better for 5 of the 8 species. Why is this so? This is so because the organic agri-environment schemes, because of the lower payments to the farmers, it results in smaller habitat areas. Can be seen here. If you compare the total area adopted by a conventional scheme, it's roughly a bit more than 17,000 hectares. The organic, slightly more than 8,000 hectares. So, but how we can explain 5? How do we explain the rest? And this is because the organic farmers adopt measure 5D in particular, and this measure 5D has a good impact on the corncrake, but also the curlew and the skylark. So we can also explain the other 3 species. Okay, key insights. The impact of an agri-environment schemes is cost dependent. Costs of measure and payment offered depend the choice of measure. And importantly, the cost structure of conventional and organic farmers differ, and hence the impact. I would just like, I understand that most of you are ecologists. Maybe that's something which would not cross your mind, but of course is very relevant if you want to understand the impact of organic farming and its interplay with agri-environment schemes. on biodiversity. So we actually see an indirect impact of organic farming on biodiversity through agri-environment schemes. Often studies analyzing the impact of agri-environment schemes also ignore that increasingly organic farmers exist together with conventional farmers, and that this has to be taken into account. Finally, I would like the modeling procedure we put in a software. There have been now versions for several federal German states like Lower Saxony, Brandenburg, Saxony, also Schleswig-Holstein. But we also applied it to 2 small regions in Belgium. Thank you for your attention.
Okay, thank you very much, Frank. So we'll open up to questions now. First of all, is there any written in?
Yes, so we've got one for James from Jake. He asks, do the input variables have to be independent from each other? I.e., in your is James in the office example, what if the time of day variable fluctuated depending on the day of week variable?
So in that scenario, I think that would affect how you built your conditional probability table. But I think the answer is no. So you can have much more complicated networks where, so that the network we saw there just had 2 layers, it had 2 input variables and 1 output, but you can have multiple inputs and the inputs can influence each other as well as influence the outputs. The only rule you have to bear in mind is that you can't have cycles because that just wouldn't work with you wouldn't be able to tell what was due to the cycle and what was due to the inputs. So the graph has to flow in one direction, but beyond that, all of the different nodes can influence each other.
Okay, thank you. And another one for James again.
Sure.
Can the Bayesian models be applied with exponential relationship data, also with categorical data, and how is confidence captured?
So I'll tackle the last one first. So confidence is kind of implicit to some extent. So you end up with a probability of a particular state for your output node. So the state with the highest probability would be your prediction, but you also have an estimate of how certain you are in that prediction from the probability. But you also, with a more complicated network, you can use things like Monte Carlo sampling, where you assign random values to the nodes based on their probabilities and then run the network lots of times to give you a distribution of the states of the different outputs. In terms of more mathematical relationships between the nodes, yes, you can do that. That's kind of starting to get into the structured equation modeling side of things. That's the sort of thing that you would do with a network that was based more on if you had a reasonable amount of data and you let the kind of algorithms in the software learn the shape of the network and the probabilities for you rather than being based on expert judgment.
Okay, thank you. So other than that, it was just comments saying great presentations and thanking the speakers. And then just to clarify a question, that the webinar will be available afterwards to access for people that have had to leave earlier. And that was it, unless anyone writes in any more while we're fielding the room.
Okay, we'll start with Peterborough, because I'm starting here. Graham?
That's a question to either and all. So these networks are quite nice that you're sort of trying to mimic the actual relationships within the environment. I'm wondering how likely it is, or the risk of either method being subject to overfitting of a model, especially if you're just feeding in sort of 1 year's worth of data into it, and how you can sort of mitigate that.
Shall I say something amazing?
With your network first?
Sure. Yeah. Okay. So,
do you want to just repeat the question?
So the question was around overfitting. So with Bayesian networks, there's certainly a temptation to put lots and lots of nodes into your network and think about all of the different things that are going on. With Bayesian networks, that tends not to work particularly well, because you end up with a network where a change to any of the inputs just gets lost in all of the different connections, and so your outputs end up very insensitive to changes in any of your inputs. So simplification is key. There's often this kind of first step is that thinking of all of the different possible things that might be going on, and then there's a stage of trying to pull out as many of those as you can whilst still keeping it meaningful.
Frank, do you have anything you want to add about overfitting?
Well, for our software, you can actually, there's a manual, quite a detailed one, so 200 pages. And as a user, you can actually go back to the logical connections and follow them up. I mean, in order to understand a specific result. You can also modify some data, for example, cost data, if things have changed, or if you think the information folder does not contain proper data or it's different in your region, you can also modify that data and then check what happens. So I think you have the software is quite good in helping people to understand the outcome and also seeing what happens if they change something.
Okay, thank you. Any other questions?
I really admire the kind of the science and the maths in this. When it comes to actually making decisions on it, nothing's ever certain. So we're never certain that James will be in the office at any particular time on any particular day. So being certain about going to see him, you can't do. So if you're trying to make decisions on the back of these models, how certain are the decision makers? How certain do they need to be before they make a decision based on what the model is talking about?
So I guess that's kind of almost a more philosophical question about modelling and decision making in general. There are ways to quantify the level of uncertainty in the model, as we've kind of talked about. I guess what I would say is that decisions will be made one way or another anyway. So some knowledge is better than no knowledge in lots of cases. But yeah, it's important to be able to clearly communicate the level of uncertainty and what the model is based on, whether it is expert judgment, and within that, the degree of agreement between experts and all of that side of things. But yeah, if the decision makers are taking the decision one way or another, this is a kind of a way to get the best that we can from the information that we have, I guess.
Yeah, I think in my experience, it definitely, the communication is so key, because if you say there's a 60% chance James is in the office, they're going to be black and white. It's Monday, 60% he is going to be there. And ultimately, they have to make a decision about whether to go to his desk or not. So they probably will on a Monday, but you have to keep kind of reminding, this doesn't mean this is necessarily true. And especially, again, that comes back to what it can and can't do, what are the caveats around this, and saying it's 60%, but we don't actually know whether it's half term. That kind of thing, you know, so you can actually, when you're doing the things, telling them what the model can't do is an important part of communication to help them understand why there is the uncertainty around it. And I think that's where the science leading into the policy really makes a key thing, because they are going to have to be very pragmatic and probably quite black and white. If there are any specific questions to the speakers today, then do feel free to email, contact, etc. And otherwise, I would like to do another thank you to all the speakers.